Hello again. In this video, we're going to go over the second part of the fundamental theorem of calculus. So here's what it says. If f is continuous on a closed interval from a to b, and capital F is any antiderivative of small f on the closed interval from a to b, then the definite integral of f of x from a to b is equal to capital F evaluated at b, which is the upper limit, minus capital F evaluated at a, which is the lower limit. So you may remember that we've talked about various ways of evaluating definite integrals. The most difficult way is to use the limit definition. We also talked about an alternative way by using the geometric interpretation of the definite integral, which is that it's the net area trapped between the function and the x-axis starting at a and ending at b. And then now this gives us a third way of evaluating definite integrals. However, there is a small limitation if we're going to evaluate definite integrals this way, and that's we need the function to be continuous on the closed interval from a to b, which is, notice the lower limit and the upper limit on our definite integral. Now, generally speaking, we work with functions that are continuous. So more than likely, in most cases, you'll be able to use the fundamental theorem of calculus to evaluate definite integrals. However, if the function is not continuous on the closed interval from the lower limit to the upper limit of your definite integral, then you can't use the fundamental theorem of calculus to evaluate the definite integral. Okay, so let me show you an example of how this comes in handy. Okay, so let's suppose we wanted to find this definite integral. First of all, notice that x squared, the graph of x squared looks like this, but notice on the closed interval from 1 to 3, it is certainly continuous. So we can evaluate this definite integral by using the fundamental theorem of calculus. Okay, so all we really need to do is find any antiderivative of x squared. Of course, there's a whole family of antiderivatives for x squared. They would look like this, x cubed over 3. Remember, you add 1 to the exponent here, which gives you a 3, and then you divide by that exponent. So it's going to be x cubed over 3 plus any constant. So this is the family of antiderivatives. Now, the fundamental theorem of calculus says we just need any antiderivatives. So you can pick c to be any number you want, and that will work. So let's let c be 0, since that's probably the most convenient thing to do. And so we're going to use f of x, or capital F of x, we're going to let it be x cubed over 3. Okay, and then all we have to do now is evaluate f at the upper limit minus f at the lower limit. Okay, so f of 3 would be 3 cubed over 3 minus f at 1, which would be 1 cubed over 3. Okay, so of course this gives us 27 over 3 minus 1 over 3, which is just 26 over 3. And that's what this definite integral is equal to. Now remember, the definite integral also gives us the net area that's trapped between the function and the x-axis from 1 to 3. So in this case, it would be the area trapped in here. And since the function's above the x-axis on this interval from 1 to 3 the entire way, this also gives us the area in this case. Not only net area, but actually the area. Now in general, remember the definite integral gives us net area. So if the function happened to go below the x-axis at some point in this interval, then remember the piece that goes below the x-axis would give us a negative contribution, and we would end up with what we call net area. In this case, since the function remains above the x-axis on this interval from 1 to 3, it actually gives us not only net area, but it also gives us the area that's trapped in here. Okay, so that's an example where we can use the second part of the fundamental theorem of calculus to evaluate definite integrals Again, we only need this function to be continuous on the closed interval from the lower limit to the upper limit. Okay, so I hope you found this video helpful. Thank you for watching. Bye-bye.